I'm JianjunYin. So today I'm going to talk about sea level rise and storm surge simulated by the GFDL climate models. Co-authors and collaborators include Steve Griffiths, Mike Wendt, Min Zhao, Laura Zena, Mike Schlesinger, and Ron Stauffer. Okay, I will begin with some background information. So in this talk, I will focus on dynamic and steric sea level rise simulated by different generations of the GFDL climate models. So these models include the CMIP3 generation, CMIP5 generation, and the most recent CMIP6 generation climate models. So because most of the climate models do not have an ice sheet component, so the land ice melt, so that part is not included in this talk. So this is something I want to emphasize at the beginning of the talk. So I will discuss the storm surge and extreme sea level events along the US, East and Gulf Coast, simulated by the latest model generation, the GFDL Cm4 and CM4 HR. So with relatively high resolution. So several weeks ago, Steve briefly discussed our recent study on the storm surge and extreme sea level. So today I'm going to provide more details on the study. So I will discuss the role of the Atlantic meridional overturning circulation, AMOC, in causing the regional sea level rise and the storm surge. Okay, so first some background information. So dynamic sea level eta here is defined as the deviation of sea surface height from the GOA. So it is closely related to ocean current, ocean circulation through the geostrophic balance. So in climate model, dynamic sea level always has a zero global mean. So basically it shows the pattern of sea level change. Both ocean density change and ocean water mass redistribution can cause dynamic sea level change. So these are the so-called steric term and mass term. So steric sea level change, so delta H rho can be calculated based on this. So based on this equation, so delta rho here is the in situ density anomaly. So you do the vertical integration from ocean surface to the ocean bottom. And the rho naught here is a reference density. So this equation gives you the steric sea level change. So the global mean steric sea level rise, so is the global average average of the steric sea level change. So A here is the ocean, global ocean area. So the so-called local steric sea level change, the prime term here is the deviation from the global mean. So the steric sea level change deviation from the global mean. So this is a local steric sea level change term. So you can see the dynamic sea level change delta eta here equals the local steric sea level change plus the mass term. So delta PB here is the ocean bottom pressure anomaly. So this term, the third term in this equation actually is indicates the ocean mass redistribution. So if you consider ocean column here, so both the density decrease or and the mass increase can cause sea level rise. So this is a steric term. This is a mass term. Okay, so the steric sea level change can be further decomposed into a thermosteric and a halosteric part. So this is the former is the temperature-induced change, and the latter is the salinity-induced change. So sometimes the dynamic sea level change can be decomposed into a barotropic and a baroclinic part. So this is the decomposition. So now let's look at the mean dynamic sea level observed by satellite. So this is the 20-year average. So you can see the complex pattern. So you can see the sea level is low in the high latitudes, and the sea level is high in the subtropical region. So if you plot the dynamic sea level along the 30-degree north latitude, so you will see the Pacific dynamic sea level is higher than the Atlantic dynamic sea level. And also you can see the sharp gradient associated with the western boundary current. So this is the Gulf Stream in the North Atlantic, and this is the Kuroshio in the North Pacific. So like many other variables, the dynamic sea level, the climate change can modify the dynamic sea level pattern in the future. So now let's look at the GFDL Cm2.1 result first. So Cm2.1 is a CMIP3 generation model. So the atmospheric model has a 2-degree by 2.5 degree resolution. So 24 vertical levels. And the ocean model is based on MOM4 and has a 1-degree horizontal resolution. So the resolution is refined in tropics. So there are 50 Z coordinate vertical layers. So the Cm2.1 model has been used to carry out the CMIP3 experiments, including the pre-industrial control simulation, the historical simulation, and also the 21st century projections on the 3 future emission scenarios. So the SRES B1, so this is a low emission scenario. A1B, so this is a medium emission scenario, and the A2 scenario. So this is a high emission scenario. So here, the upper 2 panels shows the simulated, shows the observed and simulated mean dynamic sea level. So you can see the Cm2.1 can capture the pronounced features in the observation. But also you can notice some difference. For example, the low dynamic sea level in the subpolar gyre region actually extends southward in the model simulation. And also you can see the dynamic sea level gradient across the Gulf Stream in the model is not as sharp as in the observation. So this is the mean sea level. So panel C, D, and E shows the projected dynamic sea level change by the end of the 21st century. So this is the mean anomaly during the last 10 years in 3 SRES emission scenarios. So this is A2, A1B, and the B1 scenario. So you can see in response to external forcing, so the dynamic sea level rises north of the Gulf Stream and along the northeast coast of the US and also the east coast of the Canada. And at the same time, the dynamic sea level falls south of the Gulf Stream. So due to this pattern, so the sea level gradient across the Gulf Stream actually declines. So you can see the dynamic sea level change patterns are similar between different scenarios, but the magnitude is larger in the higher emission scenario. So this pattern of dynamic sea level change is caused by the AMAC weakening. So the right panel here shows the overturning stream function in the Atlantic Ocean in the control simulation of CM2.1. So you can see the model simulate a vigorous AMAC in the control simulation. In the 21st century projection, so you can see the global temperature increases with time. So the dashed line is the global temperature time series, and different colors show the different scenarios. So you can see the warming with time. And at the same time, you can see the AMAC actually weakens. So this is mainly due to the ocean surface heating, which makes the ocean more stratified. And by the end of this century, so you can see the weakening of the AMAC ranges from 30% to 40% in the 3 emission scenarios. So this weakening actually is actually responsible for the dynamic sea level change pattern. To confirm the role of the AMAC, we also performed the so-called water horsing experiment. So in this water horsing experiment, so 0.1 sphere drop freshwater flux is input into the North and North Atlantic for 100 years. So the radiative forcing is kept constant at the pre-industrial level. So this additional freshwater flux actually can cause a similar reduction of the AMAC. And the panel F shows the resulting dynamic sea level change pattern in the horsing experiment. So you can see this pattern is similar to the change pattern in the projection run. Okay, so the dynamic sea level change pattern can be decomposed into a local steric sea level change component and a mass redistribution component. So the left panel shows the local steric sea level change in CM2.1, also in the A1B scenario, the medium emission scenario. So you can see in response to external forcing, there's an extra steric sea level rise on the offshore side of the shelf break. So you can see the above average steric sea level rise in this region. So this extra steric sea level rise is due to the ocean warming in this region in a thick layer. And this local steric sea level change pattern create a sharp gradient across the shelf break. You can see the different color so associated with the sharp gradient. So that sharp gradient can drive more water mass from the ocean interior onto the shelf region. So the right panel shows the sea level change due to the ocean mass redistribution. So we calculated this based on the ocean bottom pressure change. So you can see the increase of mass loading on the shelf region, especially on the northeast U.S. continental shelf in this region. So if you add these two components together, basically you can get the dynamic sea level change, this pattern. So the steric sea level change can be further decomposed into the local thermosteric and the local helosteric part. So local means the global mean is removed. So you can see the two parts actually compensate each other, but the thermosteric part dominates over the helosteric part. So the thermosteric effect mainly responsible for the total steric sea level rise east of North America. So the left panel shows the sea level rise at New York City. So in CM2.1, the total sea level rise is dynamic sea level change plus global steric sea level rise. So global steric sea level rise is the long dashed line. So the smooth dashed line is the global steric sea level rise. So the short dashed line is the dynamic sea level rise at New York City. So different colors for different scenarios. And the total sea level rise is this solid line. So you can see at New York City, the dynamic sea level rise is comparable in magnitude to global steric sea level rise. So it can increase the dynamic sea level rise can increase the total sea level rise at New York City. So the right panel shows the relationship between the dynamic sea level rise at NYC and the AMAC weakening. So you can see there's a good correlation between the two variables. So this is the CM2.1 result. Next, let's look at the ESM2M and 2G simulation. So these are the CMIP5 generation models. And the atmosphere is similar to CM2.1. So the ocean differs. So 2M use the MON 4.1 model. And so this is a Z star coordinate ocean model. And 1 degree horizontal resolution. 2G use the gold model. So this is the isopycnal model and also the 1 degree horizontal resolution. So this is the projected dynamic sea level change in the North Atlantic. So in two RCP scenarios, so the upper row shows the RCP 4.5, the lower row shows the RCP 8.5. So these four are the dynamic sea level change relative to the 20th century. So this four is the dynamic sea level change relative to the 19th century. So you can see the dynamic sea level change pattern is similar between the two models, although the ocean model is very different between 2M and 2G. And also the pattern is similar to the previous CM2.1 result. And also we know the mechanism actually is also similar to the CM2.1 result. So this is the CMIP5 model simulation. So next, I want to focus on the new CM4, GFDL CM4 and CM4 high-res, the model results. So CM4 is the latest generation of climate models at GFDL. So it has been used for the CMIP6 simulations. So the atmospheric model is use the finite volume dynamical core with 1 degree resolution in the standard CM4 version and half degree resolution in the CM4 high-res HR version. So there are 33 vertical levels, and the ocean model is based on the MON 6. And so this is a hybrid coordinate ocean model. So geopotential plus isopycnal. So 75 hybrid layers. And the model use the horizontal resolution is at a permitting quarter degree. So relatively high resolution. So this table lists the CMIP6 simulations with CM4 and CM4 HR. So including the pre-industrial control and the historical simulation and the SSP 21st century projection. And also the idealized 1% per year CO2 increase experiment and the abrupt 4 times CO2 experiment. So for the CM4 HR, so the both control and abrupt 4 times CO2 simulations have been performed. So in this talk, I will focus on the control simulation of CM4 and also the 1% CO2 simulation of CM4. So the result from other simulations, other experiments are qualitatively similar, similar to the 1% CO2 simulation. And the the magnitude of the change increases with the increase of external forcing. Okay, so the CM4 better represent the coastal geometry and bathymetry along the along the Atlantic coast of the US. So this is a Atlantic coastline in nature, as highlighted by the red color. So this is the right panel is the representation in CM4. So you can see CM4 roughly resolves important bays and estuaries, like the Chesapeake Bay right here. But the model resolution is not fine enough to resolve smaller bays and harbors like a New York harbor is not resolved. So I will discuss the impact of this on the simulation result later. So, and also you see the shallow continental shelf and the sharp deepening across the shelf break is realistically represented in CM4. And according to the correlation of sea level variability, so we divide the Atlantic coast into 3 regions. The northeast coast, so this is the north of Cape Hatteras. So southeast coast from Cape Hatteras to South Florida and the Gulf of Mexico, the Gulf Coast. So this is simulations of tropical cyclone TC and extratropical cyclone EC in the CM4 control simulation. So you see the panel A shows the global map of the storm track of tropical cyclones. So B shows the storm track over North Atlantic. So the contour is the subtropical high during summertime. So you can see the storm is better simulated due to the updated physics. And we probably can see Cat 1 hurricane in CM4. And we can see Cat 3 hurricane in CM4 HR, the high-res resolution. But both CM4 and CM4 HR do not simulate the strongest hurricane like Cat 4, Cat 5. So panel C shows the storm track of the extratropical cyclone EC. And so this is the storm over North Atlantic and North America. So contour line is the near surface temperature and the gradient during winter time. So you can see the strong baroclinicity just east of the coastline. So these strong storms can cause severe storm surge in CM4 and CM4 HR. So to analyze the storm surge, we calculate the daily sea level anomaly delta H in the control run of CM4. So delta H equals delta eta. So this is the daily dynamic sea level anomaly. So the so-called wind surge plus delta B. So this is the inverse barometer effect. So in all the 3 terms, the daily climatology is removed. So there's the seasonal cycle is removed. So the delta B, so this inverse barometer effect term is diagnosed based on the daily sea level pressure anomaly. So this is an example of large surge event in the CM4 control simulation. So A shows the delta eta, so the daily dynamic sea level anomaly. So contour is the sea level pressure anomaly associated with this strong tropical cyclone TC in the Gulf. So B shows the inverse barometer effect delta B, and so the total daily sea level anomaly is the sum of delta eta and delta B. And the panel C shows the storm wind, and also this line is the storm track So different color indicates different strengths of the storm at a different time. So panel D shows the storm precipitation. So you see the heavy rainfall coincides with the surge center right here near New Orleans. So this heavy rainfall can increase the surge height, coastal surge height. So panel E shows the surface current, and you see the narrow and very fast loop current. Actually, there's an eddy right here, and also the Gulf Stream, the Florida current and the Gulf Stream. So it's the current is jet-like in CM4 simulation. Panel F shows the SST anomaly associated with the cool week. So after the storm propagation. So you see the daily sea level anomaly in the CM4 simulation. This is the control. So in the CO2 experiment, so the daily sea level anomaly actually is the sum of the storm surge and the regional dynamic sea level rise due to the AMOC, induced by the AMOC, and also the global steric sea level rise. So you can think the total daily sea level anomaly in the CO2 experiment is the local and transient sea level variability superimposed on the large scale and persistent sea level trend. So this is the difference between the control run and the CO2 experiment. So let's do some model data comparison first. So this upper two panels shows the observed and simulated mean dynamic sea level. And C and D show the signal cycle of dynamic sea level. Basically, so the difference is the dynamic sea level in September minus the dynamic sea level in March. So you see the CM4 does a good job in capturing the features in the mean dynamic sea level and in the seasonal cycle. So panel E and F here is the daily dynamic sea level variability associated with mesoscale eddy. So the data is detrended and deseasonalized. So you see the CM4 actually underestimate the mesoscale ocean eddy activity along the west boundary current. So some statistics of daily sea level in the control simulation. So the left panel shows the standard deviation of the daily sea level. So you see the contour, black contour here is the 100-meter isobase. So you can see this 100-meter isobase actually separate the coastal process from the ocean interior dynamics. So this roughly separate the two dynamical regime. And the colored circle is the tide gauge data, observation data. So you see the model data comparison. So middle panel shows the skewness of the daily sea level, and the right panel shows the kurtosis of the daily sea level. So kurtosis basically measures the tiltedness of the daily sea level distribution. So high, you can see the high value, large value along the Gulf Coast right here. So that indicates the Gulf Coast is more vulnerable to severe storm surge and coastal flooding. So in addition to the moments, we also evaluate the model, the return levels of extreme events in the model simulation. So the left three panels shows the tide gauge data at New York, Charleston, and Galveston. So these three locations, and also the data is detrended and deseasonalized. And the horizontal dashed line, three horizontal dashed line, indicates the 1 in 1 year, 1 in 10 year, and 1 in 100 year return level. So the middle panels is the result, simulation result from CM4. The right panels is the result from CM4 HR. So you see at New York, this location, so the model actually underestimate the return levels. So this is because the tide gauge at New York is inside of the part of the region, is the tide gauge is the inside of the New York harbor. So this harbor is not resolved in CM4 and CM4 HR. So, and the tide, surge can be amplified by the harbor dynamics. So this is part of the region. And at Charleston, you see the return levels are better simulated by the models. And at Galveston, so you see the return levels is underestimated in the CM4 simulation, but overestimated in the CM4 HR simulation, especially for the 1 in 100 year return level. By the way, we use the peak over threshold method and the generalized Pareto distribution to calculate the return levels in the tide gauge data and the model simulation. So these are the parameters. So the higher surge in the HR, CM4 HR, is due to the refined atmospheric model resolution. So this is a comparison between a comparison of the tropical cyclone between CM4 and CM4 HR. So you see the TC actually is stronger in the HR model with stronger wind and also smaller size. And also due to the stronger wind, you see the coastal surge height is higher in the HR model. So that's the reason why you see a higher return level. So this is the time series of daily sea level anomaly at New Orleans for 1 year period. So black curve is the total anomaly. So red curve is the dynamic sea level anomaly. So the blue curve is the inverse barometer effect. So you see at New Orleans, so the large surge spikes are caused by the landfalling TC and hurricane during summertime, during warm seasons. So at New York, so you see the sea level is more active during winter time. So, and the summertime is typically the sea level is relatively quiet. But hurricanes can strike this region, like Sandy, Hurricane Sandy strikes this region. So the right two panel shows the contribution of wind surge and pressure surge to the total surge. So the horizontal is the total surge, and vertical is the wind surge, the dynamic sea level, or the pressure surge, the inverse barometer effect. So basically, you see the wind surge dominates at the two locations. So now let's look at the wind surge relationship at New Orleans. So based on the regression, so this is a typical wind pattern for the large surge event at New Orleans in CM4 control simulation. So you see when the TC or hurricane approaches the coastline, so the onshore wind actually can push water into the into the following geometry east of New Orleans. So therefore, it's a highly efficient at reaching water level in this region. So panel shape. So plot the daily wind surge height as a function of daily wind speed. So the red color is for New Orleans. So you see the wind surge relationship follows a quadratic equation. So that means when the Gulf Coast is more vulnerable, the vulnerability increases non-linearly as the storm intensifies in this region. So this panel B shows the typical wind pattern for the large surge event at New York City. So you see the blue color here, blue dots here, so show the wind surge relationship at New York. So at New York, lots surge can occur, but the surge is not that efficient as the New Orleans. So you can see the difference between the two locations. And the panel D shows the wind surge relationship at other coastal cities in the CM4 simulation, control simulation. Okay, so now let's look at the 1% CO2 experiment. So in response to the CO2 increase, so the global temperature increases and also global SST increases. So the blue curve shows the global steric sea level rise or thermosteric sea level rise. So you see by the end of the integration experiment, so the global steric sea level rise is more than 0.3 meter, more than 0.3 meter. And the right panel shows the dynamic sea level increase at coastal cities. So you see along the east coast of the US, so the dynamic sea level rise is about 0.2 meter by the end of 150 years. And the dynamic sea level also rises along the Gulf Coast, these dashed lines. But the magnitude is not as big as the East Coast. So the dynamic sea level rise is induced by the AMAC weakening in the CM4 simulation. So this is the overturning stream function in the control simulation. And this is the time series of the AMAC in the control simulation and in the 1% CO2 simulation. So you see the weakening of the AMAC with time in the CO2 experiment. So this weakening causes the dynamic sea level change in the North Atlantic. So this is the pattern of the dynamic sea level change during the last 20 years of the 1% CO2 experiment. So you see the pattern is in general similar to the previous result from the CM 2.1. But you also can see some new features like the dynamic sea level rise signal actually in CM4 extends further southward to south of Florida. And the shading is the anomalies. So the contour is the mean in the control. So the panel B shows the response of ocean eddy activity. So this is the daily sea level variability anomaly. So the shading. And the contour is the control. And you see the ocean eddy activity actually tends to reduce by the end of the simulation. Panel C shows the SST anomaly. So you see so in this plot, so the global mean SST value is removed to better show the pattern. So you see the tripolar pattern, the warm, cool, warm, this tripolar SST anomaly pattern. So in particular, the larger warming on the northeast US continental shelf in this region, north of the Gulf Stream, actually can reduce the temperature contrast between across the Gulf Stream. So can weaken the ocean front in this region. So we will see in the next slide. So this can influence the extratropical cyclone in this region. So the panel D is the ocean heat content increase, and also the global mean value is removed. So you see the maximum ocean heat content increase occur in this region, the offshore side of the shelf break. So you see the largest ocean heat content increase. So all of these changes are related to the AMOC, changes in the CM2, in the CM4 simulations. Okay, so so these are the storm changes. So CM4 simulate the increase in the storm intensity for both TC and EC. So the storm gets stronger in the CO2 experiment. For the total number, the frequency. So this plots the track density of TC. The shading is an anomaly in the CO2 experiment, and the contour is the control run. So for the TC, you see the so this is the time series of the TC over North Atlantic, the total number of TC over the North Atlantic. You see maybe there's a slight decrease of the total number of all TCs in the CO2 experiment. And also you can see in the track density map. So B here is the track density anomaly for the EC, extratropical cyclone. So you can see the reduction over the North Atlantic is more significant after 100 years. So this reduction is related to the SST anomaly pattern. So as I mentioned, so this SST pattern actually can reduce the contrast across the Gulf Stream, and also the faster land surface warming can reduce the temperature contrast between land surface and the ocean surface. So both can weaken the storm track intensity over the North Atlantic during winter time. So this is the storm changes in the CO2 experiment of CM4. So this is the histograms of daily sea level anomalies. So the left three panels shows the PI control, so the control run, and also the 1%, the idealized 1% CO2 and abrupt 4 times CO2 experiments. And the right panel shows the control run and the historical simulation and the SSP projections. So you see the increase in external forcing progressively shift the PDF to the right and towards the higher surge values. So you see the progressively shift in the three regions: northeast, southeast, and the Gulf Coast. But for the northeast and southeast coast, so this too, so the elevated surge is mainly due to the background sea level rise. So the background sea level rise is the regional dynamic sea level rise plus the global steric sea level rise in the model. But we found that along the Gulf Coast, the elevated storm surge is mainly due to the changes in storm characteristics due to the CO2 forcing, and also due to the global steric sea level rise. So you can see the overall shift of the curve, but at the same time, you can see the tail actually becomes longer along the Gulf Coast. That's due to the stronger storm in the CO2 experiment. So this is the surge. So I also plot the time series of the daily sea level anomaly at 3 cities: New York, Miami, and New Orleans. So the blue curve is the control. The red curve is the 1% CO2. So in 1% CO2, the dynamic sea level and global steric sea level rise are included. So, and also you see the horizontal line. Horizontal line is the return levels. So 1 year, 10 year, and 100 year. So, and also you see the diamond and the triangle, right? So that's the time of emergence of the anthropogenic signal. So the emergence time. So the diamond is the emergence time for surge frequency. The triangle is the emergence time for surge height. So you see the anthropogenic signal can emerge from the background variability maybe 20 years after the start of the simulation. So at New York, so this early emergence is facilitated by the AMOC induced dynamic sea level rise in this region. And at Miami, so the early emergence is due to the small background variability, small surge at Miami. But the time of emergence at New Orleans is significantly delayed. So you see this is due to the very large surge spike, the background very large surge spike. So that can delay the emergence of the anthropogenic signal. So this is so before going to the conclusion, so I want to discuss the caveats. So the model limitations. So there's no ice sheet model. So there's no land ice melt contribution to sea level rise, and there's no no impact on the AMOC, the GOA change in the model. So and also the model do not simulate tides. So there's no tide surge interactions in the model. And also in CM4 and CM4 HR, so there's no strongest storms like the category 4, 5 hurricanes. And also the model does not have a wettening and a drying scheme. So there's no inundation simulation. And also we use the daily mean could underestimate the peak hourly surge. And also there's no climate unrelated factors like the land subsidence or land uplift. So all of these factors can influence the storm surge, and sea level rise in this region. Okay, finally, conclusions. So under natural weather process, so the Gulf Coast is more vulnerable to storm surge, and the New Orleans is a hotspot. In response to future greenhouse gas forcing, the GFDL models consistently simulate dynamic sea level rise along the East Coast or the Northeast Coast in the previous model simulation due to the projected AMOC weakening. So this can increase the total sea level rise in this region and heighten the storm surge and facilitate the emergence of the anthropogenic signal. And along the Gulf Coast, so the extreme sea level storm surge is sensitive to the modification of the tropical cyclone hurricane characteristics under the greenhouse gas forcing in the 21st century. So I think that's it. I think it's on time. So so next, I don't know if there are questions. I would be happy to answer any questions.
Thanks very much. Does anybody have any questions? You can either put your hand up or type in the chat, or just unmute and ask a question. Give it a minute. Sometimes people have fumbling to unmute.
How do I ask a question? Just talk?
I think just go for it. We can hear you.
Okay. This is Alan Blumberg. I wanted to say how much I like this talk, and I wanted to ask, have you tried to tie this into what Tal Iser at Old Dominion has been working on, showing that as AMOC changes, the Gulf Stream slows down, and that pushes that bound of water that you could see through a geostrophic balance towards the coast, the east coast of the US. And I'm just curious to see how this might fit into that.
Yeah, I know Tal Iser's work. So it shows the if the Gulf Stream moves closer to the coast, that can influence the coastal sea level. And in our study, so we saw that if the AMOC, the strength changes, so that also can alter the cross-current sea level gradient. So that can cause the additional sea level rise along the coastal region. I know, so there are many similar works out there.
Thank you very much.
So we have a question from Gavin in the chat. Yeah, Gavin's asking, are there any changes in extratropical storms?
Extratropical storms. Any other changes? So the extratropical storms. So here we show that the intensity of the extratropical cyclone actually increases. That's because the increase of the SST in the North Atlantic. So increase of the SST can cause the increase of evaporation. So more water vapor in the atmosphere can release more latent heat. So that can strengthen the extratropical cyclone over the North Atlantic. But at the same time, so we know there is some opposing factor here. So you see the SST pattern here. So that can reduce the baroclinicity near the surface, and so therefore the change can reduce the frequency, actually the total number of the extratropical cyclone. At the same time, the intensity increases.
I have a minor follow-up. This is still important. Can you go back to the last slide? It's just can you show the track density plot, because it was confusing the colors and the contours.
This one?
I see an 80 in the top right in the colors, and a -20 in the contours, and a -20 in the colors. Can you just explain, are those two different things or the same thing? Go back.
This one?
Yeah. So the track density. So I see an 80 and a 40 in the contours. What's contoured versus what's shaded? Are they the same thing? Or, yeah,
so
thanks. This
contour is the track density. So I think this is the total number per decade. So the contour is the control simulation, and the shading is the anomaly in the CO2 experiment.
The anomaly of what? Sorry, I'm still confused by the
The
shading.
anomaly of the track density.
Okay, so in percent?
No, the total number, the number anomaly.
And sorry, again, the contours are what?
The contour is the total number of extratropical cyclone per decade. Yeah.
Okay.
Any other questions?
Do we have any other questions?
I have a, it's a minor point. I mean, great talk, really exciting work. For New York Bight, just a minor point is that there's no amplification in New York Harbor. There's an amplification, from Sandy Hook, from the apex, which if you resolve the water levels properly at the apex in New York Bight, there's no amplification into New York Harbor. So, but maybe you're not resolving New York Bight well enough.
The CM4, yeah, CM4 does not resolve the New York Harbor, and also does not resolve the Hudson River. I think the dynamics of the harbor and the Hudson River play some role for the surge at Lower Manhattan. So
they shouldn't change the surge from the apex in New York Bight based on observations. It should be very similar. So I would just say look and make sure that you're so it's just a minor point on the clarifying that there shouldn't be an amplification from Sandy Hook into New York Harbor, and even a decrease in the Hudson. But it's fine that you're not resolving it, but you may not be resolving New York Bight well enough. I don't know. I don't know what's going on there. But there shouldn't. If you can resolve the apex of New York Bight well enough with a coarse model, such as I've created a 5-kilometer model for that area, then it should match fairly well to New York Harbor surge, I think.
Yeah. So there's some plan GFDL is going to run an even higher resolution global model, like 1/10th degree for ocean. So maybe in that version, so the regional feature can be better resolved. Any other questions? So if no, thank you all for your attention.
Yeah. Okay. Thank you ever so much, everyone, for joining us.
Thank you.
Thank you.
Thanks, everyone.
Thank you.
For a really interesting talk, Jianjun, and I hope everyone has a great rest of the day.